Alright, so that was Holiday by Green Day. It's one of my all-time favorite songs to play on the guitar. I've been playing the guitar for around 5 or 6 years and I really enjoy it, so I decided to create a video demonstrating the physics behind the guitar today. Waves is the main area of physics that applies to the guitar. To describe the guitar simply, it is a 6-string instrument and these strings are pulled taut so that they float above the body and the neck of the guitar. Each string starts at the bridge, which is this part here, and goes all the way to the nut, which is this white part here. The string is technically a little bit longer than this distance though, because there is a little bit of string before the bridge and a little bit of string after the nut. However, this is the only part of the string that moves, so when I refer to the length of the string in this video, I'm referring to the distance from the bridge of the guitar to the nut of the guitar. And then basically all the strings on the guitar are floating strings that have 2 fixed ends created by the bridge and the nut of the guitar. And how I play these strings is I hit the strings with my right hand, which causes them to vibrate, and then I push down on different frets with my fingers with my left hand, and then this creates different notes because it changes the length of each string. Alright, so now that we've covered the basics of the guitar, let's dive deeper into the physics of the strings of the guitar. So standing waves are the waves that appear on the strings of the guitars. The definition of standing waves are a pattern that result when a group of waves reflect back and forth in a medium and constructively and destructively interfere at certain points. So constructive interference is when 2 waves come together and create a bigger wave, and then destructive interference is when 2 waves come together that are inverses of each other and they cancel out. So to demonstrate this, I have an image here. And these are 2 waves moving against each other on a string at the top. And as they move against each other, this red wave is what appears to us, and that's a standing wave. So on these standing waves, these points called nodes are created, which are the points of maximum destructive interference. So they appear still to us. And antinodes are the points between them, and they are the points of maximum constructive interference. So they appear as the crests and the troughs on the standing waves. Frequency and harmonics can be used to explain the musical notes on the guitar. For example, if I hit the open E string, it makes a standing wave. This standing wave produces the fundamental frequency of the note E and is the first harmonic of the note E. The wavelength of this standing wave is 2 times the length of the guitar string because this wave only has 1 antinode in the middle of the string, so only half the wave can appear on the string at one time. To visualize this, if you look at the fundamental standing wave in this chart, you'll notice only half of it appears on the whole guitar string, which means you would have to multiply it by 2, the length of the guitar string by 2 to finish the wave. So now that we know how to find the wavelength, how can we find the frequency, the fundamental frequency of the note E? Well, we can use the formula of velocity equals frequency times lambda. So I calculated it on my own. I found that the average velocity of a standing wave on an E string on a guitar is about 102.8 meters per second. Then I found the wavelength of the standing wave on this guitar by measuring from the bridge to the nut, which is about 62.4 centimeters. Converted to meters is would be 0.624 meters, and then multiplied by 2, like we said, to get the wavelength, which is 1.248 meters. And then all we have to do is plug it into the formula, solve for frequency, which gives us the fundamental frequency of the note E, which is 82.37 hertz. The definition of a harmonic is an overtone accompanying a fundamental tone at a fixed interval, produced by the vibration of a string or column of air in an exact fraction of its length. To represent this harmonic relationship mathematically, we can use the equation lambda equals 2L over N. N has to be an integer or else a standing wave cannot be produced. This harmonic relationship is why I can play the same note E on the same string as before with my finger on the 12th fret. The only difference is that this E note has a higher pitch or frequency than this E note, which we can hear. The reason for this is because the 12th fret is located exactly between the bridge and the nut. This means when I put my finger here, the wavelength is half the fundamental wavelength and this creates the second harmonic. So the wavelength of this E note is the same length of the string, because if you double half the distance of the string, you get the whole string. Other smaller areas of physics that contribute to the standing waves on the strings are forces, linear density, and sound. Density and the force of tension are important here because they are the only aspects of the guitar strings that affect the velocity of the standing wave produced on them. This relationship is represented with this formula, and I can demonstrate how tension affects the velocity of the standing wave by rotating the tuning peg clockwise, which changes the note of the open string, and I could lower it all the way to D. So I've lowered the frequency, as you can hear, and this happens because I decrease the tension by rotating the peg clockwise, which also decrease the velocity because they are directly related. And then because velocity is also directly related to frequency, the frequency also decreased, which is what we hear. Finally, sound is extremely important because it is how we hear all these notes coming from the guitar. When a string is vibrated, it displaces air molecules around itself, and these air molecules create longitudinal waves, as seen in this photo here. So this is the string, and it's moving the air molecules around it. Longitudinal waves are different than standing waves because they oscillate parallel to the way they are traveling. These waves are made up of regions of compressions and extensions of whatever they're traveling through. In this case, they're air molecules. And basically, these longitudinal waves of air molecules travel until they hit our eardrums, and our brain perceives them as sound. The physics of the guitar are very complicated, but this video should have covered all the basics. Even in my short exploration of the physics of the guitar, it has helped me a lot with understanding music theory and memorizing note positions and different octaves on the guitar. Overall, it has been very fun and has helped me out a lot, and I recommend all of you try it for yourself.